The sun sinks below the horizon. The serenity of night draws near. Soon the Earth will turn in harmony with the cosmos. But not necessarily in harmony with our star. The sun is sending us ominous warnings that we ignore at our peril. A roiling deep within. Energy building in its outer zones. An eruption gathering force. We are getting better and better at reading the flare-ups, the waves, and the spots that emerge on the solar surface. But our increasingly technological society has exposed us as never before to the sun's angry moods. Is the Earth ready for the next attack of the sun? The wake-up call arrived in the year 2003, with Halloween approaching. A truly scary chain of events overtook our solar system. "93 million miles away, the sun began to vent its rage. On its surface, dark regions called sunspots appeared unexpectedly, a sign of rising tension within. It had been 3.5 years since the sun last erupted in fury, at the peak of an 11-year cycle of solar flare-ups. Back then, we got ready for it by shutting down satellites that were vulnerable to high levels of radiation. No one expected this. The sun erupted in a series of massive explosions called coronal mass ejections, or CMEs. Vast electrified gas clouds raced outward. Solar telescopes recorded the action. The largest emission of solar X-rays ever seen. Flares reaching tens of thousands of miles into space. And a wave of charged particles traveling at 8 million kilometers per hour. The sun became a giant plasma weapon, more potent than any in science fiction, and pointed right at our home planet. On Earth, the Halloween storms produced some of the most spectacular auroras ever seen at the North and South Poles. They occur when a wave of charged particles from the sun interacts with Earth's magnetic field in the outer regions of the atmosphere. Beautiful and awe-inspiring, they were once identified as the dancing of spirits, or as signs from God. But as lovely a light show as this is, it means there are kilovolts of electricity in the air, looking for places to get down to the Earth. The Halloween solar storms brought jolts of electricity that impacted power grids around the world. space, they damaged 28 communication satellites and destroyed 2. A newly installed GPS-based air navigation system went down for 30 hours. This energetic surge did not stop there. Sweeping past Mars, it was so strong that it burned out the radiation monitor aboard the spacecraft Mars Global Surveyor. Ironically, this instrument was designed to study radiation that human explorers might encounter on future missions beyond Earth. Months later, the same rush of solar energy washed over the 2 Voyager spacecraft on their way to the far reaches of the solar system. Coronal mass ejections like this have been known to blast their way out to where the solar wind meets the flow of particles around the galaxy itself. The Halloween solar storm of 2003 was by no means the worst. The standard was set in the year 1859. Just after midnight on September 2nd, some campers in the Rocky Mountains were awakened, they said, by an auroral light so bright that one could easily read common print. In New York City, thousands gathered on sidewalks and rooftops to watch the light show. An observer in Havana, Cuba, reported that the sky appeared stained with blood and in a state of general conflagration. The day before, a British amateur astronomer named Richard Carrington had seen signs of what was to come. He observed an outburst of intensely bright and white light from a large group of sunspots. The eruption took aim at the Victorian version of the Internet, causing major disruptions to telegraph networks. It was a preview of the risks to our modern technological society. Like a major hurricane or an earthquake, a solar storm like the one in 1859 is a rare event with potentially significant consequences. The risks today were in stark evidence in March 1989, when a solar outburst took down Canada's Hydro-Quebec power grid, leaving 6 million people without power for up to 9 hours. Not long after, we launched the first generation of satellites designed to provide real-time data on the Sun, including the ACE and SOHO missions. Meanwhile, the threat keeps getting worse because solar events can strike at the technological networks that increasingly define modern life. Among the most vulnerable are those that rely on GPS coordinates. Then there's spacecraft, jammed with sensitive electronics, as well as astronauts. Aircraft, especially those traveling over the poles. And energy systems. To the electric power grids that bind civilization together, we are adding an array of renewable sources, including wind farms and solar arrays. This grid is getting larger, more varied and smarter. There is a microprocessor in almost every device, communicating and negotiating with one another, running everything from air conditioners to power plants. Add to that hundreds of miles of new broadband internet lines into our houses, and all those expensive smartphones tucked into our pockets. The more integrated our technological infrastructure becomes, the more vulnerable it is. A recent estimate published by the National Academy of Sciences says that an outburst like the one in 1859 could cause damages of $1 to $2 trillion in the first year alone. It's not only the cost of repairing and replacing damaged components, but also the lost business and government services extending over the years it takes to recover. To understand what a powerful force the Sun can be, take a look at Venus. At almost exactly the same size and mass as Earth, it's truly our sister planet. Scientists have found that solar winds are steadily stripping off lighter water molecules in its upper atmosphere. What's left is a witch's brew of acetic gases and carbon dioxide that have thickened at lower altitudes, rising to some 90 times the density of Earth's atmosphere. At a concentration of 95% in Venus's atmosphere, CO2 gas trapped increasing amounts of sunlight and helped drive surface temperatures up to 464 degrees Celsius, hot enough to melt lead. How did Earth avoid such a harsh fate? For one thing, our planet has a natural defense system that Venus lacks. Earth spins around on its axis once every 24 hours or so. This has an effect on molten iron welling up from deep in its core. Like an electric dynamo, these plumes of hot metal generate magnetic fields that extend beyond our atmosphere, enveloping the Earth in a protective shield called the magnetosphere. Watch what happened after this solar eruption, recorded by satellites on December 13, 2006. A simulation of the blast wave shows its truly immense reach, well above and below the orbits of the planets. Sweeping by Venus, it takes aim at our planet. The wave slams into and depletes the outer surface of Earth's magnetosphere. Plasma carried by the blast now flows by Earth. The magnetosphere responds by stretching out into a long, thin structure. While Earth's magnetic field may be strong, it's not impenetrable. When energy from the Sun builds to a critical threshold, hordes of charged particles move out along field lines, wrapping around the Earth and finally flowing in. Now channeled and concentrated around Earth's poles, these particles suddenly snap, inducing huge jolts of current, strong enough to wreck spacecraft and blow out power transformers on the ground. According to recent satellite findings, the danger is enhanced when the magnetic fields of Earth and the Sun are oriented in the same direction. With our vulnerability to these cosmic power surges growing, we have launched a whole new generation of spacecraft to monitor the Sun. They've taken up positions in low Earth orbit. They are out plying the margins of the magnetosphere. And they're circling far out in interplanetary space to get a good, clear look at changes on the solar surface. With data flowing in, scientists are drawing an increasingly complex picture of the Sun and its inner workings. Their aim is to predict solar eruptions more accurately than ever before and usher in a whole new era in space weather forecasting. What Scientists have found is that solar outbursts get their start deep within the core of the sun. The star's immense gravity squeezes hydrogen atoms. The pressure and the heat rises, causing a fusion reaction in which hydrogen atoms crash together, merging to form heavier atoms like helium. These fusion reactions give off heat, which rises in plumes to the surface of the sun. This process, called convection, is similar to streams of warm air rising into cold, forming thunderstorms. You can see evidence of convection on the surface of the sun in a pattern of ever-evolving blobs known as granules. Each blob is the equivalent of a cloud top, only it's 1,000 kilometers across. Superimposed on these is a pattern of supergranules, even larger convective regions 35,000 kilometers across. The SOHO spacecraft has recorded the effect of all this rising energy. Its ultraviolet sensors show a wavy pattern of gas on the sun's surface, along with the super-hot halo of gas called the corona. The white regions are places where the rising gas suddenly escapes. Immense loops of ionized gas, 10 times the diameter of Earth, rise and fall back. These solar prominences are hot, about 60,000 degrees Celsius. But there are times when the release of energy on the solar surface gets bottled up by magnetic fields generated by the sun's spinning turbulent core. Using data from the sun's exterior, scientists have modeled these fields as they erupt all around the sun's surface, twisting and looping. Heat rising towards the surface follows these magnetic field lines, which can also stifle the rising columns, forming relatively cool patches. That's where sunspots form. 4 centuries ago, Galileo Galilei was the first to argue that these blotches were actually on the sun's surface, though he suspected they were clouds. Their nature remained unclear until 1908, when astronomer George Ellery Hale demonstrated the link between sunspots and intense magnetic fields. Over the years, scientists have drawn their strange shapes in an effort to understand them. What they didn't see until recently was the heat and pressure building around them. Using data from the Solar and Heliospheric Observatory, SOHO, scientists are learning to read undulations on the surface of the sun, the result of pressure waves ricocheting through its volume. Like the study of earthquakes on Earth, this field, called helioseismology, is a window on the movements of gas inside the sun. It's also generating predictions of flares and sunspots, including those forming on the far side. Detectors aboard the SOHO spacecraft have managed to catch the moment when the energy kept by a sunspot is suddenly released. A shock wave travels rapidly outward, like a solar tsunami, with enough force to circle the star. That signals the start of a coronal mass ejection, or CME, a massive eruption of particles and hot gas. With a coronagraph to block out the bright light of the sun, you can see how violent our sun can get. If a CME is detected blasting out from behind this artificial eclipse, you know that satellites and power systems on Earth are going to get hit hard, especially if it has been launched in the direction of where Earth will be in its orbit in about 24 to 36 hours. The sun sends a wave of energetic particles that will crash into Earth's magnetic field. And as more and more of the ground around Earth gets carpeted with conductive metal, the chances are that all the juice will fry something vital to humanity. Fortunately, our ability to monitor the sun's behavior is getting better. The two spacecraft of the Stereo mission, launched in October 2006, have now moved into positions on opposite sides of the sun. For the next 8 years, they'll give solar scientists a full 360-degree view of the solar surface. When an event does take place, the 4 spacecraft of the Themis mission are flying wide loops through Earth's magnetic field in an effort to monitor it. What they have found is a turbulent zone where energy from the solar wind builds. They are looking for the breakpoints when a solar attack becomes inevitable. We now live in a time of popular fascination and fear of looming catastrophe. The world did not end, as many expected, at the turn of the millennium in Y2K. But 2012 is approaching. Planets going rogue. Alien invasions. Galactic upheaval. A bad moon on the rise. Those threats are the inventions of pop culture. The sun is real. Sunspots and other solar activity rise and fall in a cycle that lasts about 11 years. The 24th solar cycle since record-keeping began should reach a peak around May 2013. There are no scientific predictions of a huge Earth-beating solar flare. In fact, the Space Weather Prediction Center predicts that sunspot activity will be well below average this time. That doesn't mean the sun will go quiet. The Halloween storm, after all, happened as the last cycle was winding down. In the meantime, we do have more eyes in the sky staring at the sun. And solar storm warnings have gotten better, thanks to improvements in global alert communications. With better warnings, companies and governments can more effectively shut down or shield electrical grids and computer systems. But we are still not able to predict solar weather far in advance. So for now, it's best to hang on to your cell phone and back up your data. Let's hope that Earth is ready for the next attack of the sun.